Today I'm going to walk you through what we call Additive Manufacturing 101. Terminology here, a little bit on terminology. Additive manufacturing is known by many names: 3D printing, rapid prototyping, rapid tooling, rapid technologies. As we see, we go through. It's known by all of these different technologies. Accepted standard here with Stratasys, that we like to call it, is additive manufacturing. Additive manufacturing is a term covering all the technologies. It's a term covering all the applications, replacement for RMP or additive fabrication. Definition: collection of technologies directly driven by CAD data to produce three-dimensional physical models and parts through an additive process. Typical build: you will output an STL file or a 3D CAD drawing from your CAD system. We import that into our software and pre-process it. Does all the processing of the file, slices it, prepares it to go to the machine tool, to our machine. In the machine, we build the part, and the end here, just basically, you can use it for fit, form, function, paint it, plate it, whatever. FDM-Specific Materials. We use engineering-grade thermoplastics. ABS M30. This has been our forte, ABS, A1, 15, 20 years ago when we first started. Different formulas as we've come along, up to the M30 now. We have added other materials to this list. ABS M30i, which is a medical grade. ABS EDS7, this is electrostatic dissipation. So we use this basically for assembly in electronics, fixtures, things like this. Polycarbonate ABS blend, a little tougher. We're moving up from the ABS. Coming on down the list, Altem 9085 and polyphenol cell foam. Those are our high temp materials. The Altem 9085 is a higher heat, will withstand higher heat, and is better in areas where there might be some concern about toxicity in a fire. The polyphenol cell foam, or as we like to refer to it as PPSF, is, again, takes the higher heat, chemical resistant to gas, oil, antifreeze. Solution classes here, your additive manufacturing parts. On-demand services. On-demand services would be a service bureau, such as Red Eye or Forecast 3D that we see out here. They distribute globally. They're usually somewhere in the neighborhood 3 to 10 day turnaround average. They offer all technologies usually and all materials out there. Least expensive, probably to get a prototype part. Next up is 3D printers. They're probably the most affordable. They average about 10 to 50K, simple, easy to use, and they're optimized to give you a part for fit, form, some function. Some use 3D printer to include all technologies. We use it just on our lower range systems. Finally, 3D production systems. This is our highest performance systems. This would be our Fortis or Conic systems at Stratasys, usually in the 50 to 500K and up. They're optimized for performance, broad range of applications, many different materials, custom build styles, solutions for most applications out there, and most referred to as high-end systems. Applications for additive manufacturing. Conceptual modeling. These are models, prototypes that are used when production is being conceptualized in the beginning state of your design. Application is primarily product visualization or communication purposes for that product. And the requirements are not very demanding. Next up would be a functional prototype. Prototypes used to evaluate the fit, form, or function. We want to prove all aspects of the product, performance, or say manufacturability. So the requirements are a little more strenuous when we get to the functional prototype. Next up is manufactured tools. This is a massive growth area for Stratasys in the last few years. And what we're talking about here in manufactured tools is it's a collection of items used to produce, inspect, or handle manufactured items. Assembly line type stuff, maybe. Includes jigs, fixtures, gauges, templates, guides, patterns, some cases molds, dies, tooling. Some people refer to this as rapid tooling, rapid manufacturing, or rapid prototyping. Last is the end-use part. End-use parts are sub-assemblies or products that are sold to a customer. They are actually put into service as finished goods. So they would come straight off the machine and go into use. Somewhere sold maybe to you or somebody else. Technology assessment. As you can see here, we have the conceptual, functional, prototypes, manufacturing tools. They all work well across all the applications, be it conceptual, functional, manufacturing tools. 3D printers do great in the conceptual stage. They're fine in a functional stage, but you can see as we get to manufacturing tools and end-use parts, not so, it's a little different. 3D production systems excel there due to the different materials. The way we can build them, we can get the polycarbonates, we can get the Altems, the polyphenol cell phones. So the 3D production systems work great across all applications too, but they excel more in its manufacturing tools and higher in the end-use parts. Design cycle, where does it fit in? Well, I've just showed you it can fit into all areas of the design cycle, from the concept, detailed design, we can do tooling, and in some cases, an actual end-use part. Conceptual model. This is an example of a conceptual model. This is Ducati. They're a manufacturer of racing and racing-inspired motorcycles that has amassed a string of World Bike Super Championships. Ducati needed to reduce time to market for new products. Rapid prototypes were used in the past, but they were built mostly by service bureaus, which caused delays. Solution. Ducati purchased a Forta system and built a prototype of a twin-cylinder oval piston engine comprised nearly entirely of FDM parts. The engineers then came up with a concept for a four-cylinder L-shaped engine, and that was also prototyped in FDM. The benefits, the accuracy and durability of the models enabled engineers to physically analyze each component, recognize their design flaws in those engines, and fix them rapidly. This decreased the number of errors and sped up the design process. Development time was reduced from 28 months in the past to 20 months on these two engines. The company's previous $1 million per year euro budget for prototyping costs have also been substantially decreased. As we can see here, the processes in the lower corner, outsourcing to service bureaus, 28 months. That was just for one engine, 28 months. With the Fortis in-house, 8 months, and we see a 71% savings just in time alone to develop the one engine. They did 2 in the 20 months. Functional. This is an example of a functional prototype. Toro Irrigation Products Division makes commercial consumer water sprinklers, valves, and controllers. Golf courses use a lot of the Toro products that come from this facility. The challenge at Toro was recently redesigned a sprinkler and needed prototypes that could withstand 100 psi water pressure testing. But the machined functional prototypes used in the past were expensive and time-consuming to make. Solution, once again, Toro used a Fortis system to produce functional rapid prototypes that handle 100 psi pressures. They put these on the test stands. They ran them. The benefits, The ability to produce rapid prototypes that could be used for functional testing enabled engineers to create and evaluate new design iterations in a fraction of the time required in the past. The design was perfected at a much lower cost than would have been required in the past. Over a 2-year period, FDM technology has reduced product development by 283 weeks on a number of products. It has also reduced tooling costs and prototyping service bureau costs by $500,000. Manufacturing tooling. This is one of the largest, most expanding areas for Stratasys in the past few years. BMW. They have 3 brands, right? BMW, Mini, Rolls-Royce motor cars. They're a world-leading manufacturer of luxury automobiles. The challenge here, in the past, the company used conventional CNC machining to do hand tools for automotive assembly, testing, fixturing. Design freedom was limited, which often meant that productivity, worker comfort, ease of use, process reliability were less than optimal. Also, the cost and lead time involved in conventional manufacturing was higher than desired. The solution, BMW now uses a Fortis system to make ergonomically designed assembly aids that perform better than conventional made tools. The benefits, the freedom of design enables engineers to create configurations that improve handling, reduce weight, improve balance. The additive FDM process can easily produce organic shapes that sweep and flow, making it possible to maximize performance while improving handling characteristics. The use of FDM has also reduced the cost and time required to produce typical manufacturing tools. Here you can see, this is the actual placement tool in use that they built, and some of the other tools that they built. Headlight alignment, cubing device. I guess I kind of missed here, but let's back up a second and look at the costs here. You know, CNC machining, you have lead time. You got to get this in, you got to get an operator, you got to get skilled people to manufacture these. Cost, $420, 18 days time to get one fixture. Fortis system, we turned that around, $176, day and a half. 58% savings in dollars and 92% saving in just time to produce these. The other thing is if that gets damaged, what happens in the cycle? I got to go back into this cycle of CNC machining if it's a metal one, and here we go again. Where the Fortis, I can put it in there, have the part overnight, and move on. Manufacturing tools, some examples. Jigs, fixtures, chuck gauges, drill and rivet guides, go, no-go gauges, alignment tools, guides, tooling masters, patterns. You know, anywhere where there's assembly, I'm sure there's a use for fixture tools. Last is an end-use part, Script Pro. Script Pro builds automated pill dispensing systems. The bezel that accepts the vial for the pills at Script Pro, all of those were manufactured. They're manufactured to precise tolerances and to accept one vial size in there. So when they fill it, these bezels are specific to the vial size. Script Pro makes 56 bezels and is continually adding more. The company does not know which bezels will be needed on a particular machine until the order is placed. Expensive tooling and inventory would be required for each bezel if conventional manufacturing methods were used. Solution. Script Pro invested in a Fortis machine to build production parts to customer orders without tooling. Okay? Elimination of tooling saves the company about $25,000 per year in producing the bezels. Lead time for making FDM bezels is 1 day. Script Pro can provide faster deliveries to customers while eliminating bezel inventory. In addition, the company can add new bezels or make design changes without retooling at minimal cost. It's a drawing, right? So we go and we edit the drawing or we make a new drawing. In the CAD system, we're on our way. Direct benefits of end-use parts. They're lowering costs. Why are they lowering costs? Because there is no tooling. Shorter lead times. Why? Again, no tooling. Indirect. They get the design freedom. These bezels were constantly changing. It's easy to make another one. Here, they can make changes very easily. It isn't a major problem. Mass customization. They can customize it to the end use. It supports lean initiatives, just-in-time manufacturing, and it reduces warehouse space for tooling and parts because they don't need it. That covers all the applications that I showed you. To sum this up, additive manufacturing technologies are proven. They're integrated in many markets today. We have end users that they do their whole production on one of our larger machines, the 900. It actually goes out to the end customer. It's poised as a disruptive technology, and there's never been a more appropriate time to evaluate the benefits.